Welcome back to the deep dive. Today we are zeroing in on what is arguably the biggest bottleneck right now, the thing that's really stopping generative AI from being adopted everywhere in enterprise settings.
It's that trade-off, isn't it? The impossible trade-off between how useful large language models are and just the sheer prohibitive cost of running them in production.
Exactly. When you try to move this stuff out of a sandbox and into, mission critical workflows, the raw physics of LLMs, the latency, the infrastructure costs, it just becomes a hard stop. So our deep dive today is very focused. We're asking if small language models, SLMs, can do more than just approximate what the big ones do. Can they actually be superior?
And specifically in the domain of agentic tool calling.
Right, through very targeted fine-tuning.
And we have, well, a phenomenal source for this. It's a breakthrough paper that tackles this scaling problem head-on. The researchers present this domain-adapted SLM, and it slashes the infrastructure overhead.
Turning an OpEx nightmare into something manageable.
Precisely. But we have to start with the main finding because it completely changes the conversation. A model with only 350 million parameters achieved a staggering 77.55% pass rate on the toolbench evaluation.
Okay, just to put that in context, a 77.55% score.
It means this tiny model significantly outperformed all the baseline systems. And that includes massive 175 billion parameter models like ChatGPT. So this result is, a direct contradiction to the scaling law paradigm, at least as we understand it, for these kinds of specialized jobs.
So we're going to get into the exact methodology that made this possible and then unpack what this really means for deploying AI agents in a way that's actually scalable and accessible. Okay, so let's unpack this. Let's start with the constraints that even drove this research in the first place.
Right.
Any team trying to integrate this stuff deeply into enterprise systems, they face these huge operational hurdles. We're talking massive upfront infrastructure costs.
And the ongoing operational costs, the inference costs, they just don't stop.
And then there's the risk of relying on closed APIs.
And those risks are critical. For mission-critical systems, relying on an external API introduces so many variables you can't control.
Data privacy, for one.
Data privacy, unpredictable latency, no real guarantee of robustness. If your core business process depends on a chain of reasoning that can be throttled or changed by an external API, that system is just fragile.
So this research offers a path to kind of internalize that capability.
It does. And the central hypothesis is that SLMs, if you train and align them meticulously, can basically perform just as well, or maybe even better than LLMs, on these very focused deterministic tasks.
Like tool calling.
Like tool calling, structured automation, that kind of thing. Most of the work until now has been focused on just scaling up the parameter count.
Let's make it bigger.
Yeah, just make it bigger.
Yeah.
So there's this big unexplored gap in how to really maximize performance by specializing these smaller models.
And this idea, this pivot to specialization, it's not entirely out of the blue. It builds on some existing work.
Oh, absolutely. We've had strong signals from foundational research, like the Llama papers, which showed that smaller, well-designed models trained on really high-quality data can often match the bigger ones.
And the concept of knowledge distillation, too.
Exactly. Where you have a small student model learn to mimic the behavior of a much larger teacher model. All the theoretical grounding for this approach was already there.
Okay, so given those high stakes, the engineering choices they made here are, paramount. Let's get into the methodology. They chose the Facebook-copped 350-meter model. That's a very specific choice.
It's a profoundly strategic one. The OPT architecture is well known, and 350 million parameters is it's a critical nexus. It's small enough to be super efficient, low latency, small footprint.
That's right.
But it still has enough capacity, enough parameters to actually map complex APIs, handle function arguments, and manage the reasoning chains that you need for tool calling. It's the Goldilocks zone for this task.
And the technique was supervised fine-tuning, SFT. But the critical detail, the one they really highlighted, was limiting the training to a single epoch. Why do that?
That is the essential insight here. In normal language modeling, you might do multiple epochs to really drill in the knowledge. But here, the goal isn't to memorize facts.
It's to learn a behavior.
It's to learn a specific, generalizable behavioral pattern. By sticking to one epoch, they're forcing the model to learn the general mechanisms of tool use, instead of just memorizing the examples in the training set.
Which improves its ability to handle things it's never seen before.
Drastically. It's all about generalization to new tools and new instructions.
And to learn that behavior, they needed a huge, high-quality data set. They used Toolbench.
Yes, and Toolbench is the definition of domain-specific data at scale. We're talking about, what, 187,542 instruction solution pairs?
Wow.
And what makes it so powerful is that it's all derived from over 16,000 real-world APIs from the Rabbit API Hub. This isn't synthetic stuff. It's grounded in how real tools work.
Okay, now for our expert listeners, let's get into the nitty-gritty of the training, the hyperparameters.
Absolutely. This is where the magic happens. The learning rate was conservative, 5 times 10 to the -5, with 100 warm-up steps. You do this so you don't just destroy the pre-trained weights.
Right. And they used gradient accumulation.
They did, to get an effective batch size of 32. Crucially, though, they used aggressive gradient clipping, a max norm of 0.3.
And why is that so important?
For a model of this size on this kind of highly structured data, it's vital. It's like a safety valve. It stops the gradients from exploding and prevents catastrophic forgetting, ensuring a really stable optimization with the AtomW optimizer.
So the goal of all this was to get the model to generate a very specific structured output, the thought, action, action, input pattern.
Yes.
For anyone who isn't familiar with that in an agent context, what does that actually look like?
It's basically the agent's internal monologue followed by a command. So instead of a chatty answer, it outputs a strict sequence. First, the thought token, which is the reasoning, I need to find this data, then I need to do that.
Step by step.
Exactly. Second, the action token, which is the actual API call.getThisData. And third, the action input token, with the exact JSON parameters for that API call. The model is trained to only do this, to suppress everything else.
That focus on deterministic output is exactly what you want in a critical system. Okay, so they built this highly specialized SLM, now they have to test it.
And that brings us to the toolbench evaluation framework. This isn't just another benchmark. It's really become the gold standard for assessing this kind of tool-augmented reasoning.
And to make the comparison fair, the testing conditions were identical for all models.
Absolutely non-negotiable. All the models, the 350M, the 7B, all the way up to the 175B baselines, were run through the ToolEvil automated framework. And a key detail here is that ToolEvil actually uses ChatGPT as an unbiased evaluator, which keeps the grading consistent.
And the inference parameters were locked down.
Locked down. Max sequence length of 8192, a very low temperature of 0.1 for deterministic output, and a cap of 10 reasoning iterations. You have to be efficient.
The metrics themselves are pretty comprehensive.
They are. There are two core ones. The first, and I think the most important for scalability, is the pass rate evaluation. It's binary. Did the agent complete the task or not? Simple as that.
Just practical functionality.
Right. Then there's the win rate assessment, which is a more qualitative comparison. It looks at the quality of the solution. Was it factually accurate? Was the reasoning sound? Was it cost effective?
Let's talk about the structure of the tests, because the rigor here is what makes the results so compelling. It's 1,100 queries across 6 categories.
And the categories are designed to really stress test generalization. G1 is all single tool scenarios. G1 instruction tests new instructions for tools it already knows.
Okay.
G1 category tests generalization across different types of tools. And then the really tough one, G1 tool, tests the model on tools it has never ever seen before.
Which is a must-have for any real-world agent.
Exactly. And then the complexity just ramps up from there.
In the G2 and G3 scenarios.
Right. G2 moves to multi-tool problems. G2 instruction is about combining tools from the same category. G2 category is harder. It requires linking tools from different categories, which means you need to understand data flow and dependencies.
And G3 is the final boss.
You could say that. It's complex multi-tool use within a collection. If you can navigate these escalating levels of complexity, you've proven you have a generalizable reasoning system, not just something that memorized a bunch of examples.
Okay, so we have the constraints, the precise methodology, and this really tough evaluation framework. The stage is set. Did this tiny constrained model actually stand a chance against the LLM giants?
The answer, according to the data in Table 1, is a definitive and frankly shocking yes.
Let's just focus on the numbers. The fine-tuned SLM, 350 million parameters, gets a pass rate of 77.55%.
And the comparison data is it's staggering. Toolama, which is a 7 billion parameter model, it got 30.18%. That's a performance gap of over 47 percentage points.
And what about the big one, ChatGPT?
The 175 billion parameter ChatGPT outscored 26%. So our little SLM's improvement is over 51 percentage points higher. Even the 52 billion parameter Claude caught, it barely registered at 2.73%.
Hang on. Let me get this straight. We're talking about a model that is 500 times smaller,
500 times.
achieving a pass rate that is almost 3 times higher than a leading 175 billion parameter LLM. This is a direct challenge to the idea of scaling laws in this domain.
It is a genuine revelation, a 2.98x improvement over the state-of-the-art LLM. Okay. This isn't a small gain, it's a phase change. The parameter efficiency is just undeniable. We're talking 20 to 500 times fewer parameters than the models it crushed.
So scaling is maybe necessary for broad linguistic knowledge, but actually detrimental for focused, structured tasks like this.
That seems to be the suggestion. And that brings us to the why. Table 2 gives us a big hint. The model's success rates were incredibly consistent across all the different complexity levels. They all hovered between 74% and 80.5%,
A really narrow band.
a tiny 6.5% variance. That suggests it really captured a generalizable reasoning pattern that works no matter how complex the task gets.
So what are the researchers' theories on why this happened?
They propose 3 core reasons. The first is parameter efficiency versus dilution. A huge LLM is optimizing for everything at once: poetry, code, conversation. The knowledge for tool calling is spread thin across billions of parameters.
It gets diluted.
Exactly. The SLM, on the other hand, concentrates 100% of its capacity on one job: mastering tool calling behavior.
So all that extra general knowledge in the LLM just becomes noise for this task.
Precisely. The second factor is behavioral focus. Large models tend to be, well, chatty. They generate verbose explanations, unnecessary preamble, stuff that breaks the strict format required for a tool. The SLM was trained to suppress all of that.
And just output the thought action sequence.
Only that. Which leads to the third factor, which ties it all together: optimal parameter task alignment. The theory is that 350 million parameters is a strategic sweet spot for this task,
Big enough to do the job.
but not so big that it introduces the complexity and bloat that leads to inconsistent outputs. For this specific task, bigger is not better.
This analysis really does shift how we should think about specialized AI. But okay, let's inject a bit of sobriety. What are the limitations the researchers themselves acknowledge?
Of course, the specialization is a double-edged sword. The first big one is generalization. The model was optimized for the toolbench dataset. How it performs on a completely different set of APIs, a different ecosystem, is still an open question.
And what about contextual understanding?
That's the second one. The 350M size might limit its ability to handle really ambiguous user requests. If you need a lot of general world knowledge just to figure out what tool to pick in the first place, a 175B model might still have the edge in that initial step.
And then there's just raw complexity. Real-world enterprise systems can have hundreds of interconnected tools.
Right, that's the scalability and complexity challenge. And of course, there's training data dependency. The model is only as good as the toolbench data. Any gaps there will be reflected in its abilities.
And finally, maintenance.
Yeah, the long-term cost. This model is a domain expert. If the APIs it knows change, you have to retrain it. A general LLM might be able to adapt with just a few examples, without a full SFT run.
But even with those constraints, the implications here they're really exciting. This confirms that domain-specific optimization at a moderate scale isn't just a cheap alternative. It's a high-performance strategy.
And future work should definitely explore hybrid approaches. Imagine using a specialized SLM for the execution, but having a big LLM handle the initial, messy, user prompt interpretation. That could be best of both worlds.
So to sum this all up, the OPT350M model's 77.55% pass rate is, well, it's a revolutionary moment for efficient AI. It completely redefines the performance cost trade-off.
And the practical takeaway for you, our listener, is that this establishes a real, validated path forward for organizations. You can now deploy sophisticated, state-of-the-art AI agents at scale without the prohibitive costs that used to be the barrier.
It's the democratization of advanced agent architecture.
It really is.
Okay, so given the huge success of this targeted approach, let me leave you with a final thought to explore. If 350 million parameters is the sweet spot for tool calling, suggesting this optimal task-to-capacity alignment, how could we use something like information theory to predict the ideal minimal parameter count for any other highly structured, specialized AI domain?